Welcome to the Journey Shake Chem. Well, I'm so excited today. We get to start a new topic. And just think, we only have 2 topics left. This topic and one more. That's just incredible. I'm just amazed. You have done so well, and I'm excited for you. So anyway, you do the 2 warm-up questions to the best of your ability, and we'll discuss them in a moment. In number 1, we are solving for molality. And the reason that we're doing this is because we are going to be using some more molality in this new topic of colligative properties. And I'm actually going to use this problem when we learn how to do some of the colligative property type problems. Well, I have 5.6 grams of magnesium acetate, and as always, we have to come up with the right formula. Well, magnesium has a +2 charge, and acetate is -1, and therefore compounds must be 0, so I need 2 acetates. Well, I have to change my grams to moles because molality is the moles of the solute divided by 1 kilogram of solvent. And I'm solving for molality, so I need my moles of my magnesium acetate. Well, 1 mole of magnesium acetate, we have to add up the AMUs. And we have magnesium here, which is 24.3, and we have 4 carbons, which is 4 times 12, and we have 6 hydrogens, which is 6 times 1.0, and we have 4 oxygens, which is 4 times 16.0. And then, of course, you know I always do the math again. I have 24.3 and 4, oops, I don't need a line there, and 48.0, and 6, and 64. And when I add these numbers up, I get a total AMU of 142.3 grams per mole. 142.3 grams of magnesium acetate. And when I do the math here, I get 0.03935 moles. And to get molality, I have to divide it by the kilograms of solvent. Well, I have 250 milliliters. And you'll recall that 1 milliliter is 1 gram for water. And then there are 1,000 grams in 1 kilogram. And therefore, my denominator is 0.25 kilograms. And when I do the math here, I'm going to have 0.1574. And my answer should have 2 significant digits. And I look at the 7 and it rounds the 5 up. And therefore I have 0.16 molal of the magnesium acetate. Now for number 2, we need to understand that salts are electrolytes. And electrolytes, as we've learned before, dissociate in water. And magnesium acetate then will go ahead and form magnesium ions and 2 acetate ions. And I'm going to go ahead and use this 0.16 molal, and I have 0.16 molal here, and I'm going to get twice as much of the acetate ions. And therefore, I will have 0.32 molal of the acetate ions. And that's how you do the warm-up, and I'll be right back. Here we go to discuss colligative properties. And if you look at the very first terms and equations worksheet, it's titled Colligative Properties for topic 15. Well, colligative properties are properties that depend only on the number of particles, not their identity. So it doesn't matter what they are, just how many of them there are. And we have a variety of things that are affected by these particles. And that's why we've been talking about particles for the last few weeks. Well, osmotic pressure is affected by the number of particles. The more particles you have, the more pressure that they have. But we're not going to use osmotic pressure very much because I believe you probably got some of that in biology. Vapor pressure lowering, what I do is I write myself a little abbreviation. Vapor pressure, it goes down, it lowers. The more particles I add, the lower that it goes. Freezing point, depression. When I'm depressed, I'm down. So I have a little abbreviation. Freezing point goes down. The more particles I have, the lower my freezing point. Boiling point, elevation. And I just write BP and it goes up. The more particles I have, the more that it goes up. Well, let's look at a few substances. Let's say that I have the same concentration of a variety of different solutions. And one of my solutions is glucose. And another one of my solutions is sodium chloride. And then I have some calcium chloride. And then I have some aluminum sulfate. And of course, you will need to be able to come up with the formulas for the compounds. I will only give you names. Well, when I look at this, I see that glucose is a non-electrolyte. Therefore, it does not break up into particles, and we only have one particle. Sodium chloride breaks up. It is a salt. It will break up into its particles, and therefore I get two particles here. And I've never seen a green gas come out of salt water when I put salt in the water. I've just never seen a green gas come out of it. I'd have to evacuate my house. So it does not form chlorine, the diatomic molecule. That's nasty stuff. It just forms chloride ions. Calcium chloride forms calcium ions and two chloride ions. Therefore, we get three particles. And aluminum sulfate, I get two aluminums and three sulfates. Now, sulfate is a polyatomic ion that is sharing electrons, and therefore they will stay together. Our polyatomic ions will stay together, and therefore here I have five particles. Now, the one with the highest boiling point will be the one with the most particles. The more particles I have, the higher the boiling point goes up. The one with the lowest boiling point will be the one with the fewest particles. Then if I'm looking at vapor pressure, the one with the lowest vapor pressure will be the one with the most particles, aluminum sulfate. The one with the highest vapor pressure will be the one with the least number of particles, which would be glucose. And for freezing point, the one with the most particles would have the lowest freezing point, which would be the aluminum sulfate. The one with the highest freezing point would be the one with the fewest particles, or glucose in this case. It is important to understand that our electrolytes are the ones that are going to dissociate into particles, and they are the ones that will lower the freezing point and raise the boiling point. And this is why when we're cooking pasta and we put salt in the water, it makes the water get hotter because it's going to raise the boiling point by those two particles. And we're going to do a calculation to show you how that works. And then we also put calcium chloride on the streets or the sidewalks in the winter to lower the freezing point. Those two particles will lower the freezing point, and therefore the ice will melt. Not a huge amount, but enough to make a difference. And now we're going to work some problems and use those formulas that are given to you on the sheet. And I'll be right back. There is an example problem on the worksheet that you have, worksheet A for today. However, I'm going to use the warm-up information that we had in order to explain what is happening with the change in the temperature of the freezing point. we have to use the molality, and I'm going to use the number that we had in the warm-up, which was 0.16 molal. However, when we are within a calculation, I would normally use it 4 places after the decimal and cut it off to be consistent as to how that we've always done that. But in this case, I'm going to go ahead and use the 0.16 molal. And the constant, if you look on one side of the terms worksheet, you will see the boiling point elevation constants and the freezing points and boiling points of various substances, because these constants depend on which solvent that we are using. And primarily we will be using water as our solvent, but the same process is done if we were using a different solvent, and occasionally you will see a problem with using different solvents. In any case, I will always give you the values for those constants. Well, the freezing point depression constant for water is 1.86 degrees Celsius per molal. And then we have to look at how magnesium acetate dissociates. And we get 1 magnesium ion and 2 acetate ions. And therefore I will have 3 particles. And it's called the Van Hoff factor, or just the number of particles. That's all you need to know. And this will give me the change in the temperature of the freezing point. And that will come out to be 0.8928. And I'm going to go ahead and erase this magnesium acetate. And that is how much the change is of the freezing point. Now, water normally freezes at 0 degrees Celsius. And we said it was freezing point lowering. And therefore, I have 0 minus 0.8928 degrees Celsius. And my newest freezing point then is negative 0.8928. And then we follow significant digit rules. We look back at our original problem, and we were using that 0.16, so I need 2 significant digits. And that will be negative 0.89 degrees Celsius. That is our new freezing point for this solution. The process is very much the same, because if you notice here, our formula, the change in the temperature of the boiling point is equal to the molality times the boiling point elevation constant. That's just a big mouthful, isn't it? And the number of particles. And I'm going to have my 0.16, if I'm talking about this magnesium acetate solution that I had in the warm-up, my constant is 0.512 degrees Celsius per molal, and I have 3 particles. And here I'm going to get a change of 0.2457 degrees Celsius, because my molality cancels. And boiling point is a little bit different. I have a different rule for how our answer should be expressed with boiling point. Now, water normally boils at 100 degrees, and it is elevated, so it goes up. So I'm going to add 0.2457. Now, you can see if I was doing 2 significant digits, it would still be 100 degrees. Therefore, we are going to take our boiling points 3 significant places after the decimal and round it. So I'm going to look at the 7, which rounds the 5 up, and I get 246 degrees Celsius. And that would be my answer for the boiling point, the new boiling point for this magnesium acetate. So you can see it's a small change of the boiling point, but it is indeed a change. And that new significant digit, this is not significant digits, we just take it 3 places past the decimal and round it, because it is such a small amount. Freezing point, we use normal significant digit rules for that. And when we're doing this, again, we will have an assessment that is multiple choice, a large part of it, and your molality will need to be expressed to 4 places after the decimal and cut off, because that will be inside the calculation. And if you look at the example problem I've given you, you can see the format there. And that's how you do freezing point and boiling point of the colligative properties. And this evening you just have one side of that worksheet, and we'll talk about vapor pressure lowering tomorrow. And I can't wait to see you then. Bye!